Welcome to Math TV with Professor V. In this video, we're going to look at integration using U-substitution. If you haven't already watched the video lecture explaining the substitution rule, I'll link it here in case you need to review some more basic integrals and the foundational concepts behind U-substitution. But in this video, I'm just going to dive right in and start cranking out a bunch of examples, okay? So first, we're going to work on some indefinite integrals, meaning there are no limits of integration on these guys. Example directions tell us to evaluate the indefinite integral, and to kick things off, we have sine of rad x over rad x dx. All right, so we need to make an appropriate choice for u. One thing I notice is I have a composition of functions. I have sine of rad x, and that's popping out to me as a good choice for u because I know the derivative of rad x is 1 over 2 rad x. We can talk about that in just a second, and I see a rad x in the denominator, so I'm already feeling good about that. So let's go ahead, let's choose or let u equal rad x, and du is going to equal 1 over 2 rad x dx. Now, if you're thinking, oh my goodness, where in the world did that come from? Okay, if u is rad x, that's the same as x to the 1/2 power. And this is just such a common derivative. I tell my students you can go ahead and just memorize what it ends up being, because when you take the derivative, du dx, bring down the exponent, subtract 1 from the exponent, so now you have 1/2 x to the negative 1/2. Well, that's the same as 1 over, since x is raised to the negative 1/2 power, you have a radical x in the denominator. And then remember, when we do U-substitution, we break apart that differential dx and move it to the other side here. So that's where we get that du is equal to 1 over 2 rad x dx. Good? Okay, perfect. So I'm looking, and I always like to draw this little kidney bean here in the original integral. I have dx over rad x. And then look now at what you have for du, and you want this right-hand side to match the kidney bean. Well, it almost matches. There's just this extra 2 here, pesky little thing. So I'm going to multiply both sides by 2. And now I have 2 du is equal to 1 over rad x dx. All right, now things are perfect because I have dx over rad x, which matches what's inside my kidney bean. And then I can rewrite this entire integral in terms of u. Do not substitute some of the terms for u and then leave other terms still with x's in them in the integral. That is not well defined. You got to change it all in one step, okay? You're not in multivariable calculus yet. Don't be mixing variables in some inappropriate fashion. So we've got here integral. Instead of sine of rad x, I'm going to write sine of u. And then dx over rad x is just 2 du. So here's the du, and then I'm not going to put the 2 inside the integral. Let's put it outside where the constants belong. Okay, it'll make your integration so much easier if you get in the habit of putting those constants on the outside of the integral sign. Okay, good. Take a second, look at it, make sure everything is holding up. U is rad x, so that's where that went. Boop. Okay. Good, so let's think. What's the antiderivative of sine u? Whose derivative did you take to end up with sine of u? Be careful. It's negative cosine u, right? We're going backwards. Oh my goodness. So keep the 2 there. The constant just comes along for the ride. So we have negative 2 cosine of u, and don't forget plus c. Since this is an indefinite integral, our final answer is going to be a general antiderivative, so you need that plus c. Okay, one more thing to do. Yes, we have to replace u with rad x. So everything needs to be in terms of the variables from the original problem here. So -2 cosine rad x plus c, and we are done. All right, very good. And for all of these integrals, you could obviously take the derivative of your final answer and make sure that you end up with the original integrand. So you can always check your own work. I'm not going to because I know they're all right, but just when you're, working on an exam or something, if you have any sort of doubt, you can check. All right, let's move on to another. I'm going to give you guys a second. Take a guess what you think u should be. Remember, you want to let u typically be the inside function in a composition, and also another key is you should see the derivative of u floating around in that integral somewhere, because remember, you end up finding du. So u and its derivative need to be there. Did you think of something? Yeah, we're going to let u equal natural log of x. And that's going to be a perfect choice because du would be, well, what's the derivative of natural log of x? Do you remember? Yes, it's 1 over x dx. And look, here's my little kidney bean. Bam, right there. So we don't have to do any rearranging. We're already set up to rewrite this integral in terms of u. Instead of ln of x here, I'm going to write u. So we're going to have integral u squared, and then this entire kidney bean, look how cute, dx over x is equal to du. Bam. Oh, that's such a harmless looking little integral. So antiderivative, add 1 to the exponent, divide by the new exponent. It's going to be 1/3 u cubed plus c. And then go back, replace u with the original variable. So u equals natural log of x. So we've got 1/3 natural log of x cubed plus c. All right, very good. Now maybe you're a little rusty on those log properties and you want to move that exponent to the front. You can't do it. Sorry. If it was ln of x cubed, then you could rewrite that and move the 3 to the front. But ln of x cubed like this, no, don't move it. Leave it alone. I don't even want to write it. It's going to make me ill. Okay. All right, let's move on and look at some examples with trig functions. So here we have integral of secant squared x divided by tangent squared x dx. Now, if you haven't memorized yet your derivatives of your trigonometric functions, you're going to be in trouble because it's hard to pick u appropriately if you don't know what each of these guys' derivatives are. So already it's popping out to me. I know the derivative of tangent is secant squared x. The derivative of secant of x is secant x tan x. So I don't think that's going to be a good choice for u. Remember, when I pick u, I want to already see du somewhere in my integral. So I'm more inclined to let u equal tangent of x because then du is going to be secant squared x dx. If I did it the other way around, I'm not seeing the derivative pop up so nicely. Okay, so secant squared x dx, bam, right here. U was tangent of x. So I'm going to have integral secant squared dx, that just becomes du over, instead of tan squared x, what should I write? Very good, u squared. Okay, so everything's in terms of u now, good? Let's rewrite the integrand so it's in calculus-friendly fashion. What do I mean by that? Write this as u to the negative second power du. Because then now we're ready to roll. You're going to add 1 to the exponent, divide by the new exponent. So new exponent is going to be -1. Don't forget, you got to go backwards with those negative numbers. And then dividing by -1, same thing, just put a negative in the front, plus c. Good? Love it. Okay, let's keep cleaning things up. So we have negative, u to the negative first is just 1 over u plus c. And what was u? U was tangent x. Okay, so this is -1 over tangent of x plus c. And we know 1 over tangent of x is cotangent of x. So our final answer should be negative cotangent of x plus c. All right. Yes, you need to rewrite 1 over tangent of x as cotangent of x for your final answer. Absolutely. I would dock a point if you didn't, if you were in my class, okay? Good. Are you guys ready for something a little more spicy? Let's go for it. Example 4. Integral of 1 over t squared times sine of 2 over t plus 3 dt. Okay, so take a guess. What's a good choice for u? Remember, whatever you let u equal, you want to see its derivative or a constant multiple of its derivative floating around in that integral somewhere. So see how we have a composition here, sine of 2 over t plus 3? I'm thinking that's going to be a good choice. And remember, 2 over t is the same as 2t to the negative first plus 3. If you have a plus constant or a minus constant, always throw it in there when you're picking u, because look what happens when I find du right now. Du, let's take the derivative. You're going to bring that exponent down in the front. So now I'm going to have -2t to the subtract 1 negative second. And then the derivative of that plus 3 is just going to be 0. So now I have dt. So the reason I said to always put in plus whatever constant or minus whatever constant might be there is because its derivative will be 0. So when you find du, it's all nice and clean and taken care of. And then this can just be u, right? So slick. Okay, do we see something like this in our integral? Oh yeah, I see it. Do you see it? We have 1 over t squared dt. Look at this giant kidney bean. And that's pretty much what I have here on the right-hand side. So du is -2 times t to the negative second. That's 1 over t squared, isn't it? dt. So there's my kidney bean. How am I going to get them to match? I want that right-hand side there to match the kidney bean. So I got to divide by -2. So we have -1/2 du equals 1 over t squared dt. So now we're ready. How exciting, to change our variables and continue the problem. So here we go. We have integral sine of u. And then the 1 over t squared dt, this whole thing, I'm going to replace with a -1/2 du. But do you remember where I told you to put those constants? Put them outside. They're exiled right here. -1/2 and then du. Good. Good, good, good. Okay. What a cleanup. Look at that harmless little integral looking at us. Okay. Antiderivative of sine u. It's going to be negative cosine of u. And we already have a negative sitting out there. So now this is going to be +1/2 cosine of u plus c. Beautiful. And then go back, replace u with what it was originally equal to in terms of t. So we're going to have 1/2 cosine. U was, I'm going to write it the way it was in the problem, 2 over t plus 3 plus c. Et voila. Do you love it? That was nice. Okay. Are you feeling a little bit more comfortable? The hardest part for students is knowing what to let u equal. And if you choose incorrectly, I would say don't erase your work, just put an X through it and understand why that was not a good choice when things don't work out so you can learn from it for the next time. And then eventually you'll get to a place where you can choose U correctly pretty much every single time when you just look at the integral. You'll have that much of a repertoire built up. So just keep practicing perfectly so you can get there. Now let's work on some definite integrals, meaning they have limits of integration. So when we make our substitution, when we make our change of variables, we're going to change those limits too, okay? So first one, we have the definite integral from 0 to 1 of e to the z plus 1 over e to the z plus z dz. All right, so sometimes it's a little hard to figure out what to let u equal, and you just got to take a guess once in a blue moon. On this one, I'm going to let u equal the entire denominator, and mentally I took the derivative of the denominator and I noticed it's the numerator, so I'm feeling good about that choice. When you're finding du, remember you take the derivative of all of the terms of whatever you let u equal. So if u is equal to e to the z plus z, then when I find du, derivative of e to the z, that's e to the z, plus derivative of z is just 1, and then I have a dz. And that's exactly what I see right here. Okay, make sure you put parentheses around that e to the z plus 1. Now, only other thing we need to do is change the limits of integration. So currently these limits are in terms of z, but I want them in terms of u. So to switch them, you come back to the original statement where you defined what u was going to equal, and I'm going to substitute in each of those limits for z. So u of 0, I'm plugging in the lower limit, is going to be e to the 0 plus 0. I'm substituting in 0 for z. So e to the 0, that's 1 plus 0, 1. And then upper limit, u of 1, that's going to be e to the first plus 1, which is just e plus 1. Leave it like that. All right, good. It looks like we're ready to switch everything and rewrite our integral in terms of u. So now we have definite integral. Limits are going to be from 1 to e plus 1. This e to the z plus 1 dz, that's just my du. Okay, love it. Over e to the z plus z down here, that's highlighted, that's u. All right, cool. So what's the antiderivative of du over u? Does it help you if I write it as 1 over u du? Does it look more familiar? Why, yes, it's natural log of the absolute value of u. So we have natural log absolute value of u evaluated from 1 to e plus 1. Work on getting to the point where you don't need to rewrite this as 1 over u du. You should start just recognizing it, okay? Good. Don't forget, when you integrate, you have to have absolute value around the argument for the natural log. And then now I'm going to substitute in the limits of integration. So I have natural log absolute value e plus 1 minus natural log absolute value of 1. And then let's think here. E, that's about 2.7 plus 1, that's not a negative number. So I don't need the absolute value here. I can just write ln of e plus 1. I can change them to regular parentheses. You can't do it when you still have a variable there, but when you know for sure that the quantity is going to be positive, now we're good. And then natural log of 1, that's just 0. So this guy's gone. And that's our final answer. Leave it like that. Just box it proudly and call it a day. Okay? Good. Next example, we have the definite integral from 0 to pi of 1 plus cosine 5t squared times sine of 5t dt. Why don't you guys take a second, pause the video, and see if you can figure out what u and du should be and rewrite the integral in terms of u. I'll give you a moment. Okay, did you try it? I hope so. So we're going to let u equal 1 plus cosine of 5t. And notice I'm putting the 1 in there as well. I didn't just pick cosine of 5t. It would have worked, it just would be more work for you. So I advise against such things. The derivative du is going to be nice because derivative of 1, that's 0. Derivative of cosine 5t is going to be a negative sine 5t times 5 because of the chain rule, right? And then we still have our dt. So when you take the derivative of cosine something, it's negative sine of the same something. And then we have to apply the chain rule and multiply by the derivative of the something, in this case the 5t, which is just 5. All right, lovely. Now let's see here. I'll draw my kidney bean. We've got sine of 5t dt. This time it was just an oval, a little ellipse. Okay, here's sine of 5t dt. I want them to be matchy-matchy, so divide by -5. Negative 1/5 du is sine of 5t dt. Okay, looks good. One more thing we need to do is change our limits of integration. So lower limit is 0. U of 0, just come change it right here. Plug in 0 for t. 1 plus cosine of 5 times 0 is still 0. What's cosine of 0, people? Yes, it's 1. So this is going to be 2. And then u of the upper limit pi, that's going to be 1 plus cosine of 5 pi. Cosine of 5 pi, it's an odd multiple of pi, so cosine is going to be -1. So we have 1 plus -1, this is 0. All right, so now we're going to rewrite this integral. Instead of 0 to pi, we have 2 to 0. Then I'm going to replace 1 plus cosine of 5t with u, and that is squared. And then last thing, sine of 5t dt, right here, is equal to -1/5 du. But where do we put the constants? They're outside the integral sign, exiled. Okay. Do you notice something we can do very slick just to rewrite this integral and make it nicer? Let's flip those limits of integration and now make it positive. So we have 1/5 integral 0 to 2 u squared du. Love it. Okay, time to integrate. So add 1 to the exponent, divide by the new exponent. You're going to have 1/3 u cubed from 0 to 2. And then we're left with 1/15 times 2 cubed minus 0 cubed. So this is going to be 8/15. All right. Notice, since we changed the limits of integration, we do not go back to the original variable because everything was in terms of u here, so no need to return to t's, okay? You can just leave your answer as is, and that is correct. It's when you have an indefinite integral, the ones with the plus c, when your final answer is not a constant, but it's a function, right? A general antiderivative, that's when you have to go back to the original variable. Not for these. Not for these. Okay, did we get it right? Did you remember the chain rule? That's what most of my students forget. They forget about this 5. Okay, got a couple more fun ones. Let's see here. We have integral from 0 to pi/16 of 1 plus e to the tangent 4x times secant squared 4x. So remember what I said. When you pick u, you should see its derivative du floating around somewhere. Any guesses what u should be? It should be tangent 4x. Not e to the tangent 4x, no way. We'll talk about why in just a second. If u is tangent 4x, du What's the derivative of tangent something? It's secant squared something, and then bam, we got another chain rule, so you have to multiply by 4. Let me show you the bad idea. Why would you not want to do e to the tangent 4x? Okay, because du would be derivative of e to the something is e to the something, and then you've got this Mondo chain rule, so now I have to multiply by the derivative of the exponent, which would be secant squared 4x times 4 dx. Do you see this in the integral if this is already busy being u? No, now you've just made such a mess of things because you have an extra e to the tangent 4x in there. You know what I mean? So don't go too wild with u sometimes, where you don't want it to have such a messy chain rule when you find du that you can't make the substitution in a clean fashion. Does that make sense? And you're gonna mess it up sometimes until you get it right. Don't feel bad about it. This is a process. Okay, so let's see, secant squared 4x dx. I see it, I love it. So I'm gonna divide by 4. That way I have 1/4 du is secant squared 4x dx. Okay. Again, you need to know your trig derivatives to see that. Otherwise, you're just going to sit here staring at your paper all day. And then let's change our limits of integration. So u of 0, that's going to be tangent of 0. Tangent of 0 is 0. And then u of pi over 16, that's tangent of 4 times pi over 16. So that's tangent of pi over 4. Ooh, someone thought about us when they wrote this problem. Tangent of pi over 4 is 1. What beautiful new limits of integration we have, right? Appreciate it. So our new integral in terms of u is going to be, we've got 0 to 1. Instead of 1 plus e to the tan 4x, what do we have? 1 plus e to the u. Good. And then secant squared 4x dx is 1/4 du. Where's that 1/4 going to go, people? Yes, outside, 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 outside. Leave us alone. Good. All right, time to integrate. So we've got 1/4. Antiderivative of 1 is u. Very good. Antiderivative of e to the u, my favorite, e to the u. And this is all evaluated from 0 to 1. Good, good, good. Leave the 1/4 outside. Look at this. Some people like to, no, don't bring it in. Leave it out there. Okay, so we've got 1 plus e to the first minus 0 plus e to the 0. So this is 1/4 times 1 plus e minus 0 minus, because I'm distributing, e to the 0 is 1. And then the 1's cancel out. And all that's left is little e in the parentheses. E times 1/4. So e over 4. Classy little answer, huh? So nice. Okay, good. I just got a couple more for you. Are you feeling more comfortable? If I were you, I would rework these afterwards and make sure you can do them by yourself without me walking you through step by step. Okay, example 4. We have integral from 0 to natural log of rad 3 over 4. That's the upper limit. Maybe I should scoot it over so you can tell. Don't be scared. You're going to be glad that's the upper limit in just a moment. And then we're integrating 4e to the 4x dx over 1 plus e to the 8x. Okay, you may have no idea where to start. So I'm going to try to rewrite the integrand so perhaps the substitution, the appropriate substitution, will be more obvious to you. I'm going to rewrite it as 0 to ln of rad 3 over 4. This is still going to be 4e to the 4x dx over, check this out, 1 plus e to the 4x squared. Isn't that the same thing as e to the 8x? Yes, it is. Do you see something that we could let u equal that you also see its derivative floating around somewhere, right? I do. If u is e to the 4x, then what would du be? Well, I'm going to have to use a chain rule, right? So derivative of e to the 4x would be e to the 4x times 4, and then we have a dx. And bada bing, bada boom, that's exactly what's there. Love it. So we've got now du over 1 plus u squared. Cool. Let us change our limits and then get back into action. So lower limit is 0. U of 0 is going to be e to the 0, which is 1. U of ln of rad 3 over 4 is going to be e to the 4 times ln of rad 3 over 4. Bam, bam. Cancel party. Then we have e to the ln of rad 3, which is just rad 3. So our new limits of integration are going to be from 1 to rad 3. Good. This was like extreme makeover. Is that show still out there? Look at how our integral has transformed. Nearly unrecognizable. Okay. So at this point, you just have to have memorized some basic, derivatives so that you can now know your antiderivatives. So antiderivative of 1 over 1 plus u squared du is going to be tan inverse of u. Just got to memorize that sucker. Sorry, there's no way around it. Okay. Yep. So we've got tan inverse of u evaluated from 1 to rad 3. Okay. So that's just something you should memorize and recognize. And then now it's time to evaluate it at the limits of integration. So we've got tan inverse of rad 3 minus tan inverse of 1. Don't embarrass yourself by trying to grab your calculator right now. It's really just shameful. So tan inverse of rad 3, imagine your unit circle. Tan inverse is restricted between negative pi over 2 and pi over 2. So we're going to be in quadrant 1. When is tangent equal to rad 3 at pi over 3? Minus, do you know when tangent is equal to 1? At what angle? Why, yes, it's pi over 4. Okay, pi over 3 minus pi over 4, common denominator is 12, right? So we have 4 pi minus 3 pi over 12, which is pi over 12. Don't even think about giving a decimal answer. No, exact only, okay? Cool. Last example. It's advanced, okay? So here we go. We've got definite integral from 0 to 1 dx over 1 plus rad x to the 4th. And you might be saying, okay, I know you're talking about U-substitution in this whole video, so I know we got to do it, but I don't see what to let u equal so that there's a du, because all that's going on right now is we've got this 1 plus rad x. So let's just go for it and then see what happens. Sometimes you just have to pick something for u and then just play the problem out and manipulate it so it works out in your favor. So this is u. We're going to let u equal 1 plus rad x. So what's du? Well, the derivative of 1 is 0. And then at the very beginning of the video, remember I told you could just memorize the derivative for rad x. It comes up so much. 1 over 2 rad x dx. And you might be thinking, Professor V, I don't see that in the integral. And you told me we need to see du in there. I know, but sometimes we have to do something a little sneaky. So all I see over here is a dx, which I got, great, but they need to match and they don't right now. So let's just move the 2 rad x over. So 2 rad x du equals dx. All right. But I'm still not happy because I just made a big deal earlier, right? How you can't be mixing variables. You can't have this rad x and du at the same time. So when that comes up, every now and then you have to go back to what you originally let u equal, that statement here. So u is 1 plus rad x. Can you solve for rad x in terms of u? Yeah, just subtract 1, right? So rad x is equal to u minus 1. I just moved this 1 over there. You see that? Okay, so that means now on the left-hand side, instead of 2 rad x, I'm going to write 2 times this, u minus 1. Yes, yes, yes. U minus 1 du. That's equal to dx. Okay, and before you fuss that now things have gotten out of control, it's going to work out really nicely. Just bear with me. So that's dx. That's going to go in the numerator, and then now I have plain old u in the denominator. So here we go. We've got integral. Instead of dx, we have 2 u minus 1 du over, what's in the denominator? This is all just u to the 4th. Beautiful. Okay, take a step back. Marinate on it for a second. Good. Okay, let's switch the limits of integration. Right now they're in terms of x. So remember, u is 1 plus rad x. So u of 0, the lower limit, 1 plus rad 0, that's 1. And then u of the upper limit, 1, 1 plus rad 1, that's 2. So my limits are now from 0 to 2. Okay? Good. What should we do next? We'll get this constant out of here. Move it outside. What was it doing inside anyways? So 2 times integral from 0 to 2. Now we have u minus 1 over u to the 4th du. And from here, it just takes a little bit of manipulation and we're ready to integrate. Notice I only have one term in the denominator. That means I can split up the terms in the numerator and write each of them over u to the 4th. Do you remember doing this when you first learned how to integrate? No? Okay, well, now we're doing it again. Okay, so I can write it as u over u to the 4th minus 1 over u to the 4th. You can't do that when there's more than one term in the denominator. So that's why we had to do this u sub, right? You can't split this guy up when it's 1 plus rad x to the 4th, but once it's just a single u, then yeah, you can split it up, okay? Good, so now let's rewrite everything. We have 2 times the integral from 0 to 2. U over u to the 4th, that's going to be u to the negative 3rd, minus, this is u to the negative 4th du. Ooh, so fun. Okay. So now we're going to integrate, add 1 to each exponent and divide by the new exponent. So we have here 2. Adding 1 to negative 3 makes it negative 2. So if I divide by that, that's the same as multiplying by negative 1/2. Adding 1 to negative 4 makes it negative 3. I'm going to divide by negative 3. That's going to switch that to a positive 1/3 u to the negative 3rd. And then this is evaluated from, you know what, I wrote the wrong lower limit. Got too excited. Was it bothering you? This should be a 1. Holy moly. 1, 1, 1, 1. Shame on me. Okay, we got it. We got it. From 1 to 2. Okay, good. Time to plug them in. So we've got 2 times upper limit. We've got negative 1/2 times, I'm plugging in 2 for u. So 2 to the negative 2nd, that's 1 over 2 squared, that's 1/4. Plus 1/3 times, now plugging in 2 for u to the negative 3rd, that's going to be 1/8. Yeah, are you with me? Okay, minus, oh, and then 1 is so easy to plug in. This is just going to be negative 1/2 plus 1/3. Okay. Here we go. So we've got 2 times negative 1/2 times 1/4, that's negative 1/8, plus, this is 1 over 24, distribute the negative, plus 1/2 minus 1/3. Okay, Common denominator time. Common denominator is 24. So I'll multiply the first fraction by 3. This one's good. Multiply by 12. Multiply by 8. Over 24. Okay. The 2 and the 24 can cancel. This is just a 12 now. And then let's add these up. So -3 plus 1, that's -2. Plus 12 is 10. Minus 8 is 2. So we've got 2 over 12. Yes? Yes. And this is 1/6. Woohoo! We made it. So, hope this video was helpful. Give it a thumbs up if it was. Share it with your fellow classmates or whoever else you think would benefit from it. And let me know if there's any other sort of integration tips and tricks that you need help with. But I do have playlists going through all of Calculus 1, 2, and 3 lectures where I explain more concepts. I just wanted to make another video where I'm just kind of cranking out problems for you guys. So if you like this sort of video, let me know. I can make more where I just bust through a bunch of examples. All right? Happy studying!